is Autoencoders. First of all, I will give you a brief introduction about the neural network and its architecture that we are presenting, that is autoencoders. Then after, our group member Vishal will present about the architecture in a detailed fashion and its architectural representation. Then our group member Sachin will present about the hyperparameters and processing part. Then Ashish will talk about the real-time example. Our base paper is generalized autoencoder, a neural network for dimensionality reduction. By dimensionality reduction means the techniques that reduce the number of input variables in a data set. So coming back to the intro part, neural networks are the functional unit of deep learning and are known to mimic the behavior of the human brain to solve complex data-driven problems. Okay, so autoencoders were first introduced in the 1980s by Hinton. Autoencoder is an unsupervised artificial neural network that learns how to efficiently compress and encode data, then learns how to reconstruct the data back from the reduced encoded representation to a representation that is as close to the original input as possible. Autoencoder by design reduces data dimensions by learning how to ignore the noise in the data. So basically, autoencoders are simple learning circuits which aim to transform inputs into outputs with the least possible amount of distortion. Now over to you, Vishal.
Okay. First, I am giving the glimpse of what is happening there. The input goes through the encoder where it is compressed and stored in the layer called code. Then the decoder decompresses the original input from the code. The main objective of the autoencoder is to get output identical to the input. Note that the decoder architecture is a mirror image of the encoder. This is not a requirement, but it's typically the case. The only requirement is the dimensionality of the input and output must be the same, and the dimension of the code, which is also known as the bottleneck, must be less than the input. The output portion of the autoencoder decodes the information that has been stored in the hidden layer in the encoded format. An autoencoder reconstructs the input that is as close as possible to the input, ideally same as input. This is the reason why the output and input dimension must match. And coming to the next slide, this is a typical figure of the both of the autoencoder. Figure A represent the actual representation of the autoencoder, while the figure B is the vanilla autoencoder, which consists only one hidden layer and one input layer and one output layer. A typical example of for any neural network. Now I think next Sachin will explain the hyperparameters.
Okay, so hyperparameters are those which we define before the processing of the model. So there are four hyperparameters. First is the code size. It represents the number of nodes in the middle layer. So smaller size means the more the input image will be compressed. Then the number of layers. So we can have as many layers as we want. And then is the number of nodes per layer. So number of nodes per layer, as is visible from the bottleneck representation of the autoencoder. So it decreases from the encoder to the code and then increases back to the decoder. Uh, we can the number of layers we can increase, and more depth can offer us more reduced computational cost for some functions, and can also sometimes lead to better compression than compared to shallow or linear autoencoders. And then is the loss function. So we generally use cross entropy or otherwise mean squared error for the autoencoders. In the next slide. So here is the processing part. So here the symbols have the usual meanings. W is for weights and B is for bias, and sigma is the uh, activation function. So first we go from the encoder to the code. So for that the function is h is equal to sigma times sigma is the activation function, w weight times x, that is the input layer, plus b bias. So we get the code part, and then from the code part we move to the decoder. That is the x dash, that is the output layer, is equal to sigma dash, the new activation function, into w dash h, new weights into the code plus b dash bias. Then we calculate the loss function. Loss function is the difference between the output layer x dash and the input layer x. So we try to minimize the difference between the two. And the next Ashish will explain the real-time examples.
Yeah, thank you, Sachin. Now we will see some real-time examples of autoencoder. The first is image coloring. In this application, autoencoder is used to convert a black and white pictures into a colored image, or we can convert a colored image into a grayscale image. Second is feature variation. It extracts only the required features of an image and generate the output by removing any noise or unnecessary interruption. And next is dimensionality reduction. Dimensionality reduction is the process of reducing the number of features that describe some data, and the reconstructed image is the same as our output, as our input, but with reduced dimension. It helps in providing the similar image with reduced pixel value. And next is denoising image. In this, the input is given to autoencoder uh, is not the raw input but a corrupted version of it. A denoising encoder is trained to reconstruct the original input from the noisy version. And next is watermark removal. It is also used for removing watermarks from image or to remove any object while filming a video or a movie. Okay, next slide. These are the references we have used. Okay, thank you.